So good morning. Today we're going to continue our conversation about reproductive anatomy, and in particular we're going to finish our conversation about embryonic development and revisit the diagram that we started on Tuesday. So when we left each other on Tuesday, we had something kind of like this. Basically, we were looking at embryonic tissues in both males and females. So again, between weeks 0 and 5, we're going to have primary development of those embryonic tissues. So we can just call that tissue development. Here between weeks 1 and 5, or 0 and 5. So if you were to examine a patient who is pregnant, you would basically be unable to tell her whether she had a male or female up to about week 6. So this is what we see again up to about 6 weeks of embryonic development. And of course what we have here is a couple of tissues. This is the Wolffian duct. And just behind that we have a precursor for female reproductive tract, that is the Mullerian duct. And this tissue down here, which connects both the Mullerian and the Wolffian duct, is the urogenital sinus. And finally, we have these tissues here. This is the indifferent gonad. All right, so this is again the basic structure that we're going to see during this tissue development phase up until about 6 weeks of embryonic development. And so again, in the genetic male, we're going to have an XY chromosome, a chromosomal profile. And on this Y chromosome, males are going to express a gene called the SRY gene. And this makes a factor called testes determining factor, or TDF. And so in the genetic male, all genetic males are going to have conversion of the indifferent gonad into the testes. So we can start to differentiate these tissues again at about 6 weeks of age. So we're going to have here differentiation of the indifferent gonad into the testes. Again, this is in the genetic male, so what we have to have happen prior to that is basically expression of this testes differentiating factor. So we can draw this structure in. And now the indifferent gonad is the testes. And one of the things, of course, that the testes will start to produce is testosterone. This is going to come from the Leydig cells. And what's interesting about this period of time is even though the Leydig cells are present in the testes, in the fetal testes, and they are able to produce testosterone, we actually don't have establishment of the hypothalamic connection until about 15 weeks of age. So this is the hypothalamic pituitary axis, which is established at about 15 weeks of age, which means that the testosterone production, which is happening during this period of time, is actually independent of any pituitary regulation. So there are local factors which are going to be contributing to testosterone production during fetal development that we don't see during adult development. So again, the testes will have Leydig cells. They will produce testosterone. They'll also have Sertoli cells, which will produce a factor called anti-Mullerian hormone. also called Müllerian inhibiting hormone. Again, coming from the Sertoli cells. And what that means is that shortly after establishment of the testes, shortly after establishment of Sertoli cells, and coincident with this expression of the anti-Müllerian hormone here, or Müllerian inhibiting hormone expression here, we're going to see essentially a degradation of the Müllerian duct. So the Müllerian duct will no longer be present in the genetic male who has expression of Sertoli cells who are producing this Müllerian inhibiting hormone. So basically what we get is a regression of the Müllerian duct. And in the presence of testosterone in particular, which will bind to the androgen receptor present here in the Wolffian duct, we see maturation of the Wolffian duct. Here, maturation of the Wolffian duct, and again, this is in response to an increase in testosterone production from those fetal testes. So testosterone is going to bind to the androgen receptor, of course, and activate the androgen receptor present in the Wolffian duct, which is going to induce the maturation of that Wolffian duct into tissues such as the epididymis, which will surround both of these testes. It's going to induce the maturation of the Wolffian duct into the vas deferens. And we'll see appearance of the seminal vesicles. Again, all with just testosterone. Again, this is in the genetic male who has testes that are producing both testosterone and that Müllerian inhibiting hormone. The last thing that happens is we have maturation of the urogenital sinus into the prostate. And external male genitalia, so the penis, the scrotum, etc. And this has to happen in the presence of dihydrotestosterone. The prostate requires a more potent androgen, so essentially we have to take testosterone, again produced by the fetal testes, and convert it in the presence of that enzyme 5-alpha reductase into dihydrotestosterone. So again, we're going to have expression of the androgen receptor here. Excuse that pencil. Androgen receptor expression here in the prostate and in the external male genitalia. But of course, we also have to have co-expression of 5-alpha reductase to get conversion of testosterone into dihydrotestosterone to get full maturation of the male reproductive tract. Of course, we described conditions in which we have a 5-alpha reductase deficiency in that case study that was presented by Catherine. An interesting look into what happens if you're just missing this particular enzyme, but everything else is relatively functional. You have internal male genitalia, but external female-like genitalia. So all of this process happens fairly early on. We have maturation, let me put this in a new color, maturation of the urogenital sinus here. In the male reproductive tract. And again, all of this is occurring prior to the establishment of that connection between the hypothalamus and the pituitary gland by those GnRH containing neurons. the last thing that needs to happen is we basically take this reproductive tract, these testes will descend, so they move down towards the external male tissues and find their place inside the scrotal sac. This happens also under the control of testosterone, and it will happen right at about 30 weeks of fetal development. This pencil's broken, I'm going to just write it here. So testicular descent should also happen prior to birth. Again, all of these processes are primarily determined by testosterone, except for development of the testes. This will always happen in the genetic male that expresses the Y chromosome. So the next thing that we should discuss is basically what happens in the female. And so we can think of it, and I obviously don't like to say this, it's not very nice, but essentially the default condition is to be female. So that in the genetic female who has an X chromosomal profile, we expect to see no differentiation of the indifferent gonad into testes. We essentially have differentiation of the indifferent gonad into the ovaries. And in the absence of that Müllerian inhibiting hormone, which would normally be expressed only by Sertoli cells, instead of having regression of the Müllerian duct, we actually have persistence of the Müllerian duct. And in the absence of testosterone, we have maturation of that Müllerian duct into the fallopian tubes, into the uterus, and finally into the cervix. This is quite possibly one of my worst diagrams, but you'll get the picture. We'll draw this again. So this was the uterus. This is the cervix. And these are the fallopian tubes, or the oviducts. Fallopian tubes. All right, so this is, again, sort of the default condition where we have no testes determining factors, so we get differentiation into the ovary. We have no Müllerian inhibiting hormone, so we have differentiation of the Müllerian duct, or retention of the Müllerian duct. We have no testosterone, which means we have regression of the Wolffian duct and maturation of the Müllerian duct into tissues such as the fallopian tube, or the oviduct, the uterus, and the cervix, which means we have one last tissue that also differentiates in the absence of testosterone, and more specifically dihydrotestosterone. And that is the external female genitalia, which would include things like the vagina, and other female external parts. So this, again, is sort of a default condition where in the absence of the Y chromosome, in the absence of testosterone, we have female genitalia. So in another example of this is in the genetic male who happens to have an androgen receptor deficiency. What you would expect to see is in that genetic male still differentiation of the indifferent gonads into testes. However, the rest of the tissue would appear to be female. Okay, so that's the basic process for both male and female in terms of sexual differentiation that happens prior to birth. And so one of the things I'd like to focus on now is basically taking a deeper look into what happens in the female. And so we just mentioned some of those processes. Again, we're going to have fetal tissue maturation or tissue development in the genetic female just prior to about 5 weeks of age. We're going to have the indifferent gonad in this genetic female become the ovary or the ovaries. We're going to have maturation of the Müllerian duct in the absence of Müllerian inhibiting hormone, in the absence of testosterone. And because we don't have testosterone to support the Wolffian duct will regress. That says regression. Finally, what we'll have is a differentiation or maturation of that urogenital sinus into the external, into the external genitalia that appears female. So again, this is the progression of the process in the embryonic or fetal female. One of the things that I'd like to discuss today is basically what's happening in the ovaries. So this again happens about prior to 15 weeks of age, again prior to establishment of that pituitary hypothalamus axis. And so today what I want to discuss is again this process in the ovary, and this is a process we refer to as oogenesis. Okay, so the process of oogenesis basically is going to involve, very similar to what we saw in the male, these primordial cells. These are oogonia. And so, like we saw with spermatogenesis in the male, we're going to start with sort of an immature cell type. Here we've got oogonia. In the male we had, of course, spermatogonia. And in steps of mitosis and meiosis, again, like we saw in spermatogenesis, we will end up with multiple oocytes again, sort of synonymous with the spermatocyte that we saw in males. This oocyte is going to be surrounded by flat epithelial cells. These epithelial cells are called granulosa cells. That's Granulosa, granulosa cells. And also surrounded by a basement membrane, or we can refer to this as a basal lamina. So that's the basic configuration of the follicle at the end of oogenesis. This is called the primordial follicle. And again, it is going to be established during the embryonic period, so prior to prior to birth, we'll see establishment of these primordial follicles. In essence, we'll have a population of primordial follicles which will then be recruited on a regular basis. So if we looked at the follicle pool in females, this is 7 million, 5 million, 1 million, and half a million. So this is follicle number, again in millions. We'd see that a majority of the follicles are established again here at birth, so that our follicular pool is dramatically increased to roughly 7 million total follicles prior to birth. Again, this happens between about 15 and 20 weeks of age of embryonic development, but even prior to birth, we have a massive amount of depletion of these primordial follicles that essentially undergo death because they didn't pass quality control checks. So that even at birth, we have about 2 million, 1 to 2 million follicles. So a significant amount of follicles have already died, have already been depleted from our reserve pool. And then subsequent to this, we'll have basically depletion of the pool over time. 50 years is about the average age of menopause, somewhere between 40 and 50 for women, and that means that essentially at menopause that we're no longer undergoing the menstrual cycle, we're no longer really releasing primordial follicles, and we'll talk about the menstrual cycle in a moment. So over time, we're depleting this pool of follicles on a regular basis, such that by the time we hit about 30, there's approximately 25,000 follicles available. And then the rate of decline goes quite precipitously from there, so that at about 50 we have roughly 1,000 follicles. During this period of time, from about 30 to 50, we have enhanced recruitment of follicles. I'll talk about the recruitment process in just a moment, but we'll basically, there's sort of a regulation of follicle recruitment on a regular basis, and that is enhanced after about age 30. So this is ovarian reserve. Which again is established during embryonic development. It is not replenishable. We start at birth with the number of follicles that we'll have for our entire life, and that these follicles will be depleted on a regular basis. So let's talk about that process by first looking at the organization of the uterus, of the ovary and its relationship to the primordial follicle. And other follicles that we'll find in the ovary. So I'm going to diagram out the ovary, and I'm going to make it large to just accentuate some of the cell types that we're going to find in the ovary. Of course, the ovary is going to be surrounded by a oviduct or a fallopian tube. This looks somewhat like a catcher's mitt, which will lead to the uterus. So the oviduct or the fallopian tube. All right. So in our ovary, we have basically some stages of follicular development. So this primordial follicle is the earliest stage follicle. It's the one that we just diagrammed out. It has the oocyte surrounded by the flat granulosa cells. As a matter of fact, at this stage we have approximately 8 granulosa cells surrounding our oocyte. And of course we have that basal lamina keeping this follicle contained. So this is again the primordial follicle. And it's approximately 0.3 millimeters in diameter. And so what we'll see is that basically on a regular basis, we think of female menstrual cycle as being roughly 28 days. We can think of this as sort of that cycle that we have this recruitment of primordial follicles on a regular basis. We will advance these primordial follicles to a next stage or phase of development, and on a regular basis we will recruit about 1,000 follicles into this developmental process. So we have again several million follicles in waiting depending upon our age. And each roughly month, we're going to recruit a new pool of primordial follicles, again, about 1,000 follicles into this developmental process. And this developmental process is going to be comprised of basically an increase in granulosa cell content. This oocyte remains exactly the same. And as a matter of fact, the oocyte of the primordial follicle and all the stages that we're going to discuss is actually arrested in meiosis, specifically in prophase of meiosis. So it's a quiet being at this point. It's not really doing anything. All of the changes that are happening that we're going to discuss happen in the cell types which surround the oocyte, which are supporting the oocyte. So what we see is basically the appearance of a structure called the zona pellucida, which surrounds the oocyte at this first stage. And this zona pellucida will, Z-O-N-A-P-E-L-L-U-C-I-D-A, I believe. That may just have one L. Who's counting? So this zona pellucida will surround the oocyte for subsequent stages. It's going to be an important part, in fact, of the fertilization process. So the zona pellucida, again, appears in this first, after this first recruitment stage. And the other thing that happens is the granulosa cells undergo a differentiation and proliferation process where they become cuboidal. They still surround in close proximity to the oocyte. The granulosa cells are going to be a supportive cell type to the oocyte, and they'll be very important for our discussion of estrogen production in a moment. Of course, we still have the basal lamina that surrounds this follicle. I'm going to probably stop drawing the basal lamina, but you can imagine that it'll be there in subsequent steps. And so there's significant changes here in this primary follicle, which included the appearance of the zona pellucida, the change in the granulosa cells so that they become more cuboidal. They actually proliferate. So now we have, we've gone from about 8 granulosa cells up to about 60 granulosa cells. So there is a significant amount of proliferation in those granulosa cells. But what's interesting is that essentially not all of the primordial follicles are able to become primary follicles. They just don't have the capacity to do so. They, for some reason or another, they just are unable to advance, and basically they undergo cell death or atresia. So that we significantly reduce our number of follicles really at each step that we're going to talk about via this process of atresia, where you remove the less capable follicles from the process, and that essentially we'll start with 1,000 and we're going to end with 1 or 2 at the very end. So we have massive atresia that happens at the primary follicle stage. We're going to have massive atresia that happens after the primary follicle to the secondary follicle stage. Massive atresia from the from the secondary to the tertiary phase. And at the tertiary phase, we still have our oocyte. It's the same, it's still arrested in prophase of meiosis. We still have the zona pellucida which surrounds it. We have a greatly increased granulosa cell content. Surrounding this oocyte, and we have the appearance of a new layer. This is a cell type called the fecal cell, which is going to surround the oocyte, or close to the granulosa cells. So this is again a new layer called the fecal, THECAL. And so in this tertiary follicle, we again have a few important changes, one of which is the appearance of this fecal cell layer and the expansion of the granulosa cell compartment. So that now our tertiary follicle is increased in size. So our primary follicle was about 0.6 millimeters, so basically a doubling from the primordial follicle. Now our tertiary follicle is about 0.4 millimeters, so it is greatly increased in size. It also is increased in granulosa cell content, so now we have about 15,000 granulosa cells. We've gone from 8 granulosa cells to 15,000 granulosa cells, and of course during this process we've lost a significant amount of follicles along the way, so that now we end up with, at our tertiary follicle stage, about 200 follicles. So we've already significantly depleted our follicular pool just in this initial few steps of recruitment and some physical changes that are happening to this follicle. What's interesting is that this entire process, I'm going to denote it by a line, is hormone independent. Which means that it does not rely on LH, it does not rely on FSH to advance, which also means that this process happens throughout our life, even prior to puberty, even prior to the establishment of that kisspeptin containing population, the establishment of the pulse generating apparatus by those kisspeptin containing neurons. And so that we can have recruitment of primordial follicles. Even in a 5-year-old girl, she'll have recruitment of primordial follicles. We'll have advancement to a primary follicle, advancement to a tertiary follicle, but in the absence of LH, in the absence of FSH, in the absence of that pulsatile activity of the GnRH containing neurons, the pulsatile activity of those kisspeptin containing neurons, we cannot go any further than this thecal cell stage, so that in the 5-year-old girl, all of these tertiary follicles, I think I said thecal cell stage, tertiary follicle stage, all of these tertiary follicles will die by atresia in the absence of LH or FSH. So only after puberty can we move forward from this tertiary stage to the next stage. And of course, not everybody is fit to do so, so we will undergo, these follicles will undergo atresia if they are not fit to move forward. So this begins our hormone-dependent phase of development. The oocyte is still in arrest. It hasn't progressed beyond prophase 1 of meiosis. We still have the zona pellucida. Again, it's going to be an important aspect of fertilization, so it still needs to be there. We have a greatly expanded granulosa cell content around this follicle. It's basically, the granulosa cells are going to continue to proliferate throughout this developmental process. They are a supportive cell type, once again, for the oocyte, and they are an important component of hormone production, and we'll talk about those aspects in a moment. We still have the thecal cell compartment, but what's happened is that there is a space that's formed between the granulosa cells and the thecal cells. And I said that I would stop drawing it in, but I just want to re-emphasize that we do still have this basal lamina that's surrounding this follicle. Okay, so I have to apologize because my video cut out and I just kept on going. So I'm going to, rather than start over again, since this is actually my second hour of recording this video, I am going to just use this as like a cooking show. So essentially what we had happen is the formation of, again, this large antral compartment. So because of the formation of this large antral compartment, which happens to be a very fluid-filled and hormone-filled compartment, we call this the early antral follicle. Our granulosa cell compartment has increased substantially, so that we've gone from 15,000 granulosa cells up to about 75,000 granulosa cells. The size of this follicle is also greatly increased from approximately 0.4 millimeters up to 1 to 2 millimeters in size. Over the next several stages, we are going to undergo, or the follicle will undergo, massive amounts of atresia once again, so that at the very end, when we have this very large follicle, this follicle that has an extremely large antral compartment, 60 million granulosa cells, and a thecal cell layer that has increased quite substantially as well. This particular follicle, this very large follicle, we refer to as a pre-ovulatory or Graafian follicle. We've essentially gone from our start of about 1,000 primordial follicles, and at the end there really is only 1 or 2 Graafian follicles, which are exquisite enough to have made it through this hormone-independent phase and made it through this hormone-dependent phase to get to this final stage, this pre-ovulatory stage. And so what that means is that this Graafian follicle is going to be the follicle that will ovulate the oocyte. And so we'll talk about that process probably in our next lecture, the process of ovulation, where we release this oocyte into the oviduct. That's again going to be a hormone-dependent process, and it's going to rely upon the activity of the thecal cells in in particular. But both the thecal cells and the granulosa cells are going to be important for hormone production. So I'd like to spend a few minutes at the end of this lecture just talking about how the thecal cells and the granulosa cells are contributing to hormone production, in particular in the production of estrogen. Okay, so if we diagram out our granulosa cells in relation to our thecal cells, of course the granulosa cell compartment is going to be quite large, especially in that Graafian follicle. We had something like 60 million granulosa cells. Our thecal cell layer is going to be separated in large part from the granulosa cells by that antral compartment, so I'm going to make a space between the two. And somewhat synonymous to what we discussed with the testes in the male is that the granulosa cells and the thecal cells are going to be expressing Okay, so somewhat synonymous to what we discussed in the male testes is that the granulosa cell and the thecal cell are going to express a different complement of receptors. So we'll actually see the thecal cell expresses the LH receptor, so it will be responsive to LH, which means that when we get binding of the LH receptor by LH, we're going to, of course, increase pKa. The LH receptor, as we discussed in the male, is a GS-coupled protein receptor, so we get activation of cyclic AMP and an increase in pKa. And as a result of this activation of pKa, we're going to see a couple of important changes. Of course, these are changes that we've discussed in other cell types, such as the steroid hormone-producing cells in the adrenal gland, such as the testosterone-producing cells, the Leydig cells in the male testes. We'll see an increase in cholesterol esterase expression to liberate cholesterol from its cholesterol ester. We'll see an increase in expression of that star protein, which delivered that free cholesterol to the specialized mitochondria that we see in these thecal cells, the specialized mitochondria that we saw in the Leydig cell, and also the steroid hormone producing cells in the adrenal gland. We'll also see an increase in the LDL receptor, which brings in the cholesterol ester for steroid hormone production. Of course, we're going to require an abundant amount of cholesterol to actually synthesize steroid hormones in tissues such as the thecal cell, in tissues such as the Leydig cell. And so in the presence of STAR, in the presence of enzymes number 1, 2, 3, 6, and 9, we can actually make in the thecal cell testosterone. So the thecal cell is going to be producing massive amounts of testosterone in response to LH activation of its receptor. Of course, you know that females don't actually have large amounts of circulating testosterone in their system, which means that we're going to have to do something with this testosterone to convert it into the circulating hormone that females do have in abundance, that's estrogen. Of course, we've already learned that enzyme aromatase can take testosterone and convert it to estrogen. So aromatase is actually expressed by the granulosa cell, so that in the presence of testosterone, the granulosa cell can produce massive amounts of estrogen. So you would anticipate that in that antral follicle, either the early antral follicle, a late antral follicle, or the Graafian follicle, that these follicles are going to be producing a large amount of estrogen. Also synonymous to the process that we saw in male reproduction in those cell types, the Leydig cell and the Sertoli cell, this granulosa cell is the cell that expresses the FSH receptor. So it is responsive to FSH. And binding of FSH to the FSH receptor is going to induce a couple of very important changes in this local environment. One, it will increase the fluid content in the antrum. Two, it's going to increase the expression of a protein that we've talked about in the past. That's IGF-1. IGF-1 increases a couple of things. It increases the proliferation of the granulosa cell. It increases the expression of the FSH receptor. Both of these things are extremely important, not only to increase the abundance of the granulosa cell through increased proliferation, but also to increase the level of the expression of the FSH receptor. And I'll explain to you exactly why this is important when we talk about the endocrine changes in the female in next lecture. However, I'll just mention to you now, just to set you up, that basically over a follicular phase, over the early part of the menstrual phase in females, FSH levels are going to be declining, but the follicle is going to depend very heavily on FSH for advancement. And so in the endocrine environment where FSH is declining, we're going to have to increase the level of FSH receptor expression. So this is going to be dependent upon IGF-1 in particular. All right, so one of the last things that I want to discuss today is essentially one more protein hormone that's going to be released from the granulosa cell, and that's also in response to FSH receptor activation. This is a product called inhibin. And in fact, FSH receptor activation in the granulosa cell increases inhibin, but also FSH receptor activation in the Sertoli cell in the male increases inhibin. And inhibin is going to be an important component of the negative feedback effect on FSH. So inhibin will act back on the gonadotrope cells to decrease FSH release from the gonadotropes. So it's part of a negative feedback loop that will contribute to what we'll see are the endocrine changes in the female. We also see the same thing in the male, but it's going to be very important for this process for our discussion of follicular development. And that inhibin is going to be significantly reducing the amount of FSH available in the body. So I'm going to leave our discussion here, and we'll pick up with our next lecture talking about those endocrine changes that are going to happen over a follicular cycle. And then we'll also discuss what happens with ovulation, as well as what happens in the presence if sperm happens to be present in the oviduct and we get fertilization in the process of pregnancy. So thank you, and I hope you guys have a terrific holiday, and I'll see you back in class on Monday.